Alrighty, so we've talked about regular momentum, and now we're going to talk about momentum for something that's rotating, and that is going to be called angular momentum. So the first thing I want to do is really compare the linear or translational stuff with angular stuff. So we're going to go through first what we've already learned, and then at the very bottom here, we're going to talk about what's new. So we have mass, and the equivalent for mass when we're talking about rotational stuff is moment of inertia. Because when we're trying to make something just move in a straight line, mass is what matters. But when we're talking about making something rotate, it's not only the mass, but where the mass is. Because as the mass is farther away from where it rotates, it's going to be harder to make it rotate. And the two equations that you guys needed to know so far for moment of inertia is mr squared and 1/2 mr squared. So for mr squared, it was if you have an object going around in a circle, think like a planet going around the Earth or something like that, or a rock on a string that you're swinging around your head. It's also mr squared when you have a hoop, think like a hula hoop, or something where all the mass is on the outside, maybe like a bike tire. And then the 1/2 mr squared is for a solid cylinder, or a disc, or a pulley, something where you have all the mass filled in here. All the rest of the moments of inertia that you need to memorize are on page 210 of your book. So either you will have access to your textbook to use those, or on a test, you'll be given the other equations if you need them. So you do not need to memorize any of the other ones. For velocity, we talked about velocity in a straight line. That was just v. Angular velocity is omega. I think of it as like two v's that are swoopy. To remember that that's the symbol for angular velocity. So the equation for velocity was change in position over change in time. When we're thinking about, well, what would the angular equivalent would be? Well, instead of talking about how far something went, we can talk about how much it rotated. So how far it rotated. And so I don't want you guys to memorize another equation. Instead, I would like you to remember velocity and then be like, okay, so that's velocity. Angular velocity would just be the angle instead of the distance or displacement. And then to get between velocity and angular velocity, we did this thing with the circle. And we said, here's the radius. This is our angle theta. And then the distance that it would rotate if I were to take a measuring tape and measure out here, that is my distance x. Or if you're in calculus, it's s for your arc length. But the main thing here is finding the relationship between these. And so we realize that your angle times the radius is going to be equal to that distance x on the outside. So I think of it as you multiply the two near the middle and you get the one on the outside. So that's our angle, and that's our linear, like translational distance traveled. Instead of angle, I could do angular velocity times my radius, and that's going to be my regular velocity. I could also do my angular acceleration times my radius, and that's going to give me my angular acceleration. So all three of these came from that circle, and this is the one right here that we're going to be using, and that's what I've written right here. Now, if you take both sides and divide it by r, you get this. So this is going to be a little bit more helpful. For me, I have a hard time remembering this one, so I remember the v equals my angular velocity times radius. The next thing I want to talk about is net force versus net torque. So net force makes something go in a straight line. Net torque is going to be what causes something to twist. So force versus torque. And so when we did these, we had our sum of our forces is equal to mass times acceleration. And instead of mass, when we're talking about torque, we do the equivalent of mass, which is moment of inertia. Instead of acceleration, we're doing angular acceleration. So again, you don't need to memorize a new equation. You just need to remember these equivalencies. Instead of mass, it's moment of inertia. Instead of acceleration, it's angular acceleration. And lastly, Instead of momentum, which is what we did last time, we are going to learn about angular momentum. So regular momentum was little p. Angular momentum is capital L. So momentum was mass times velocity. Instead of mass, now we've got this moment of inertia, and instead of velocity, we're going to have angular velocity. So pretty straightforward. This is the equation that you're going to want to write down for today. Alrighty, so the first thing I want to do is go ahead and go over an example. So here I have a conservation of angular momentum problem, and it really is the same as linear momentum. If I have something rotating, I have a certain amount of angular momentum, and after the collision, I need to have the same amount of angular momentum. So here I have two disks with a radius of 10 centimeters. The bottom disk has a mass of 3m and is at rest, and I drop a second disk with a mass of m on top of it. As you are dropping it, you give it a little spin so it is rotating with an angular velocity of 12 radians per second. After the top disk lands on the lower disk, they both rotate together. What is the new angular velocity of the disks? So this one's just sitting on something totally frictionless where it'll be able to rotate once this one lands on it. And this one I'm dropping kind of like when you spin a top or a dreidel, you spin it and it's going, and then you spin it as you're dropping it, and then it's going to fall and hit this one. So this one was spinning, this one's not spinning. And then after I do that, then they're both going to spin together. So the first thing I want to do is go ahead and make a angular momentum bar chart. So before the collision, all the angular momentum was in the top one that was spinning. And the bottom one did not have any angular momentum because it was not rotating. So when I think about my mass times my moment of inertia times my angular velocity, that'll just be 0. So that's why this one's 0. And then afterwards, both of these are going to be rotating together. Because if you think about it, one can't spin any faster or slower than the other if they're stuck together. One of my examples for this is if I give you a watermelon and tell you to run down the street holding the watermelon needs to go the same speed as you are. You can't have your watermelon go faster or slower than you are, because if you're holding on to it, it needs to be going the same speed as you. Otherwise, you're not holding on to the watermelon anymore. So if I know that both of these have the same angular velocity, then I know that the one with more mass is going to have more momentum. So in this case, more angular momentum. Alrighty, so then what I'm going to do next is I'm going to think about this in terms of my conservation of angular momentum equation. So I'm going to add these two on the left together and have that equal the two on the right. So I'm just going to add these like this. And so that's how I get this equation up here. So I have my angular momentum of the first one plus the angular momentum of the 3m1, and that's going to be equal to my angular momentum afterwards. So I'm adding the angular momentum of the little one plus the big one together. So here I have, instead of angular momentum, now I'm putting in the equation for angular momentum. So that's your moment of inertia times your angular velocity for each of them. And then I went ahead and substituted in the equation for moment of inertia. So in this case, they are a solid disk. So I know that it's going to be 1/2 mr squared. So this one was just a mass of m, so I got mr squared. This one here has a mass of 3m, that's why it's 1/2 3mr squared. So I plugged all that in. And then here I put in all the numbers for my radius. My initial angular velocity was 12, and then more radii. Okay, and then here I multiplied these numbers together. So 1/2 times 0.1 squared times 12 is 0.06. 1/2 times 0.1 squared is 0.005, and 1/2 times 3 times 0.1 squared is 0.015. So in my next slide, what I'm going to do is I'm just going to move this up so that way it kind of follows along. Okay, so this is the line that we just had. So next, what I'm going to do is I'm going to realize that all three of these m's are in all parts of this equation, so I can divide everything by m. And then add these two together. So 0.005 plus the 0.015, and I get the 0.020. And then my answer I will get is 3 radians per second. So divide both sides by the 0.020 to get 3 radians per second. So this is really pretty straightforward. And then the next thing that I'm going to do is an example with something that does not seem like it should have angular momentum. So watch that video next.